We're on to section 7.4. Now, I've said in the previous videos for this chapter, there is no new maths here, I'm just doing examples. Now, I'm sticking to that. That's true, there is no new maths, but these examples, we are going to apply the maths that we know in situations which is so difficult that it perhaps seems as though it's new at first. These, from here onwards, really, section 7.4, 5 and 6, this is where the really nasty questions come from. And unfortunately, this is where most of the exam questions come from. Well, not most of them, but a lot of the exam questions look like these. We're not to panic about it, though, because at first they seem hard, but when you've done a few of them, you will get into the rhythm of it, you'll get into the habits. They might not seem easy at first, but when you've done enough practice, like the questions we've done earlier on this chapter, they just start slotting into the same techniques. We use the same techniques every time, we write down the same sort of equations all the time, so they're not going to be too bad. So don't panic if this is the first time you've seen these and you're thinking, oh my goodness, that looks really difficult. Get into the exercise, get practicing, and you'll get there, okay? Now, we're dealing with static objects still, and in this case, well, not in this case, in every case, every time you hear the word static, you think equilibrium. Every time you think equilibrium, you think the forces balance out, the resultant force is zero, and the second thing you think is the moments balance out. Clockwise moments equals anti-clockwise moments. There is no turning going on, so there is no overall turning effect, okay? Those are the two things that we know. So far, we've only been using the first one of those two facts. In these questions, we need to deal with some moments as well. Now, there are a couple of situations here in example 7 and example 8, which come up again and again and again. I think we could think of them as both the same sort of thing, really. Particularly example 8, though, comes up an awful lot, which is a sort of ladder problem, okay? But first of all, let's deal with one of these ones, which is, I don't know what we call these, a stick resting on a pivot sort of a problem, I suppose. So it goes like this. We've got a uniform rod, it says. This is example 7, page 142. A uniform rod of mass 40 kilograms and length 10. So everything that we read is going to help us. A uniform rod means that the mass, the centre of mass is in the centre of the rod. So there's my rod, the length is 10, so 5 metres off the ground, not 5 metres off the ground, 5 metres up the rod off the ground. There is the weight, and the weight is 40, that's the mass, times g. So 40g pushing down. You know what, I'm going to go straight for a bigger diagram, because we're going to need it, I think. So 40g pushing down. We have the end of the rod is on rough horizontal ground. So this is how we're going to deal with rough and smooth here. There is going to be a reaction at the ground. We can split it up into a vertical and a horizontal reaction. Okay? So if you push down on the ground at an angle, so here's the ground, let's say I'm pushing there on the ground, then there will be a reaction from the ground, and there might be a friction force pushing back on me. So there will be a reaction that will push back some in this sort of direction, right? In the sort of up and rightwards direction. Now, rather than thinking of this as one reaction force on this rod, we're going to think of it as a reaction from the ground vertically and a friction force horizontally. Or you can just think of this as the vertical and horizontal reaction. So sometimes we'll label this RV and RH for horizontal, or RX and RY for horizontal, X and Y direction reactions here, okay? I'm going to put it on now as a reaction and a friction, but those two, you could think of them as one force pushing kind of that way, or you could think of them as a vertical and a horizontal parts of that force. We'll go that way for now, though. The rod rests against a smooth peg, so we've got a peg here. Now, if this peg is smooth, there is no friction. So this is not providing a reaction force, well, the reaction force comes at 90 degrees to the surface, which is at 90 degrees to the peg. Now the peg we can think of it as a circle, and this is a tangent to the circle, so 90 degrees to that is acting sort of this way, isn't it? If there is a friction force on the peg, then we could think of it as one reaction force which is going kind of in this direction, and we could split that up into a reaction and a sort of friction force along the line of the rod. But in this case, we're just going to have this reaction force here. I'm going to call it, oh, I'll use, there you go, they've called it N for normal reaction, normal meaning another word for perpendicular. I'm just using an N because that's the notation they've used in the book. Okay, so we've got a smooth peg, goes that way. If we had a rough peg, we might want a reaction and a friction force, which in this case would be stopping this rod sliding down, so the friction force would go up there. The rod rests in a smooth peg, where A to C is 8 meters, so that means we've got 2 meters here. Remember, this whole thing is 10 meters long, so 5 meters to the middle, 2 meters there, so this bit must be 3 meters. The rod is in limiting equilibrium at an angle of 15 degrees. That means that this friction here is going to be mu times that reaction there. So I'm going to put that straight in on my diagram. You could write that in as a separate equation. Angle of 15 degrees to the horizontal, 15 degrees. So that means that this angle here is 15 degrees. Find the magnitude of the reaction at C and the coefficient of friction between the rod and the ground. Okay, so what can we do? We can say that upwards forces equals downwards forces, right? We can balance the forces out, okay? And then we can also take moments. Now, in the book, they've taken moments first, and then they've then they've done the forces afterwards. Well, how are we to know that that's the most efficient way of doing it? Basically, we don't know that that's the most efficient way of doing it. We're just going to have to work with what we've got. So what I would do naturally here is to think about forces first, and then to think about moments second, and then look at the equations and see which one gives me the right answer. Perhaps if we thought about it enough, I'd be able to see which one was going to give me the answer first, but it's just, I don't think it's worth stopping and thinking. I think we can go straight into the equations. I'm going to just think about this here. I've got a 15-degree angle here. Okay, so that makes this angle here 75 degrees. This one and this one make 90, so this one here must be 15 degrees as well. Okay, and that will help me because I want to split up this N into vertical and horizontal components. So I'll think of it like that. Okay, a vertical component and a horizontal component. So I'm going to go vertically. What are my upwards forces? I've got an R here. I've got an N. This has got a bit messy, hasn't it? There we go. N cos 15. So dealt with that one, dealt with that one. This one here is pushing downwards. I've got 40 G pushing downwards, and this mu R is pushing horizontally, so nothing vertically. Horizontally, that's vertical, so we ignore it. Mu R pushing to the right. This one is vertical, so it's not pushing left or right. This one is going, has got a horizontal component to the left, so 15 sine, N sine 15 degrees. There's equation 1. There's equation 2. I've only done 2 of the 3 things that I can do, so let's take moments. I'm going to go for moments about the bottom here because that's where I can most easily picture this thing turning, and also it's got 2 forces going through it, so I'm only going to have a turning force, a moment here and here, aren't I? These 2 don't make this thing turn around this point because those 2 forces go through that point. So moments about the point that I've just labelled A. Well, that is going to be 5 meters times by the component of this force which is acting that way, okay, which is 40 G cos 15 degrees. If you want to see it the other way, extend the line of that force. It is 40G times 5 cos 15. So 40G times this distance here, and this distance here is 5 cos 15. Either way, it's 5 times 40G times cos 15. So that's the moment from that force, and that is, imagine it pushing down, a clockwise moment. That is equal to the anti-clockwise moments. Well, not that, we've got 4 forces, dealt with that one, dealt with that one, dealt with that one, this one to go. So that is 8 meters times N, because that N is already at 90 degrees, so this is the perpendicular distance to the line of the force, so 8N. Equation 1, equation 2, and the N there is normal reaction, it's not a Newton's. Equation 1, equation 2, equation 3, and now whatever they ask us, I should be able to work it out from here, so let's look at it and see if we're right. The magnitude of reaction at C, so N is the first thing I want, and if we look at the equation, look, there it is, N will pop out of this equation, because the only thing I don't know in that equation is the N. Then it's asking us for the coefficient of friction, so it's asking us for mu. Well, mu is in this equation, I know n, I don't know r, but this equation here, if I know n, then I'll be able to find r. So I still with equation 3, substitute the answer into equation 1, substitute the answer from equation 3 and from equation 1 into equation 2. In other words, take these 3 equations and solve them simultaneously, and that will get us to the answer. Now, example 8 is a ladder problem, and these are some of the fiddliest ones here, so I'll do that in a separate video since we're already at 10 minutes. Good luck with example 7.